All right, guys, welcome to our second video on thermodynamics. We call this thermodynamics number 2. It's going to really be a review of our first one, but because I think thermodynamics, that's like my favorite subject, that's kind of why I wanted to do 2 videos, just to make sure that we have a full, complete understanding of this concept. Says, oh yeah, tough guy, what are you going to do about it? He's a blind guy to the Grim Reaper, accidental suicide. All right. Guys, first law of thermodynamics. This is a great Jeopardy. If you guys ever make Jeopardy, that could be a question. First law is energy can't be created or destroyed. I think you guys know that, right? Energy just changes form from light to heat to sound, so forth. Therefore, the total energy of the universe is a constant. Energy can, however, be converted from one form to another, and that's what we're talking about, okay? Spontaneous processes. Those are ones that proceed without any outside intervention. Like, for example, the only way you would have a gas here just collected in one is if the valve was closed. But if we open it, spontaneously what's going to happen is the gas is going to fill. So this process is spontaneous, but the reverse process is not spontaneous. Processes that are spontaneous in one direction are non-spontaneous in the reverse direction. What's a spontaneous reaction or process? The rusting of iron, right? Iron comes in contact with oxygen. Obviously, if it's a moist environment, you're just going to accelerate the rusting process. So that's, but to the reverse process, so the oxidation, which is what we call rusting, is spontaneous, but the reverse process is not. Now, we could chemically go from this process to this, but that's, remember, to be spontaneous is without any outside intervention. Like they're talking about, what are they talking about here? Oh, they're talking about ice melting, right? And you guys remember we talked about this because we'd already introduced Gibbs free energy. The question is, would, does ice melt? Well, what is it? Remember, a lot of these things depends on temperature, right? If it's above 0 degrees, it will melt. If it's below 0 degrees, it won't melt. So we'll look at the Gibbs free energy equation again. Entropy, you guys remember, is randomness or disorder. I wouldn't worry about that. So you guys see how I purpleize this. Hopefully you guys can tell the purple apart from the red. You guys can write down anything. I encourage you to write down anything you want, but the purple is what I would say is definitely what you want to have in your notes. Remember how do you get the delta S of a process or a reaction? You take the entropy of the products, the final, minus the entropy of, the entropy of the final minus the entropy of your initial or your reactants. Second law of thermodynamics states the entropy of the universe increases for spontaneous processes. What we're saying here is the second law of thermodynamics says basically the universe is getting more and more disordered, right? You guys, it's kind of like, think about, once again, your bedroom is kind of like a microcosm of the universe, right? Your bedroom just kind of, over time, just kind of gets messier and messier. What I have a problem with this is, particularly with the individuals that think that the world, the universe, its development and its existence can be explained purely from natural means is, well, that being said, what can explain the order, the complexity, and the beauty that you see in the world around us if everything's kind of going to a more and more decayed, disordered, random state? I think that's a strong evidence for the existence of God. Like, you think about it. We talked about our room. Does that mean your room can't be cleaned? Of course your room can be cleaned. You can do the reverse process. The spontaneous process is for your room to get messy. But you can obviously undergo the reverse process, but what's necessary to do that? It's not just like time, matter, and energy, because that's what the naturalist would believe, that that's all the universe consists of, is time, energy, and matter. But you think about it, time, energy, and matter wouldn't be enough to clean your room. I mean, you could put energy in there, you could heat up your room. It's not like everything is going to become organized. What's needed? It's an intelligence. It's a intelligent mind, right? And it's your intelligent mind that goes, oh, these socks, they go in the sock drawer. Oh, these undies, they go in the undie drawer. So I would argue that you need an intelligent mind, and that would be really the only real explanation for why we have order in a universe in which the second law of thermodynamics is true, that apart from any kind of external help or influence, things will tend to go toward a state of disorder and randomness. Just a little something to think about. You guys just kind of want to provide different thoughts, but obviously we're focusing on the science. So there's different kinds of motion. There's translational, right, moving from point A to point B. There's vibrational. Think about in the solid form, molecules will vibrate. And then there's also rotational. So those are all different kinds of movement. And you guys, that would be associated with entropy. The more options for molecules to move, you might imagine that the higher the entropy value of those particles. Entropy increases with the freedom of motion of molecules. That's essentially what I'm saying. So therefore, the entropy of gases compared to that of liquids compared to that of solids, typically the entropy of gases will be greater than the entropy of liquids, which is greater than the entropy of solids, right? We talked about if you dissolve, a substance in water, the solid is dissolved in a solvent, you're going to expect the entropy to increase, right, as those now dissolved particles are able to be more disordered and freely move about. In general, entropy increases when, now there's several things here, I just kind of wanted you to mainly get the ones in purple, when gases are formed from liquids and solids, and then entropy would also increase when the number of moles of a substance, or in particular a gas, forms. So like in this situation, we have, 3 gas molecules would react in atoms reassemble into forming 2 gas molecules. In this case, this process, this forward reaction, we would say, or forward process, we would say the entropy decreases. We went from 3 gas molecules to 2 gas molecules. Third law of thermodynamics, another Jeopardy question. The entropy of a pure crystalline substance at absolute zero, you guys remember, think about it. What's absolute zero? That's 0 Kelvin. You guys remember that's the lowest possible temperature. And what's the lowest possible temperature? If temperature is a measure of the average kinetic energy of the molecules, and obviously as matter loses heat energy, molecules slow down, and they're going to keep slowing down until the point at which they stop. Wouldn't that be the lowest possible temperature? That's 0 Kelvin. What do you guys think the entropy of a substance at 0 Kelvin is if there's no molecular motion? You guessed it, it's 0. Okay, so every substance has an entropy value assigned to it. We had talked about that, and we had used it in the first thermodynamic video. So, you guys, here's a list of some things. Hopefully, you guys would look. You see some entropy values for solids, entropy values for liquids, and entropy values for gases. And as expected, what do you guys notice? In general, the entropy values of the gases are larger than that of the liquids, which in turn are generally larger than that of the solids. But there's another thing you want to take into account is the size of the compounds. You guys can see, look, within the solids, as the atoms get bigger, the entropy values get larger, right? You think about larger atoms, more protons, more electrons, a lot more variability, potential for disorder, randomness, and the same thing with the liquids. And so so there's a relationship between the entropy value and its state of matter, and also the size of the substance. Standard entropies tend to increase with increasing molar masses. Larger, more complex molecules tend to have greater entropies. 1 carbon hydrocarbon, 2 carbon hydrocarbon, 3 carbon hydrocarbon, 186 joules per mole, 229, 270, and you see as it gets larger entropy values. Okay. Once again, this is just showing if we want to calculate the delta S, the change in entropy for a system, we always take the products minus reactants. Same. Oh, notice this, guys. You guys will see this little not sign. That indicates a standard. That's when we have that means it's under standard conditions. And when we're talking about gases, that would be gases are a pressure of 1 atmosphere. And if we were talking about solutions, we'd have a concentration of 1 molar. So that just means standard conditions. It says, when you were a pup, I had a tracking chip implanted into your skin. Oh, so I don't get lost? No, I'm just nosy. Your parents implant a chip into you guys. Okay, you guys, this is Gibbs free energy equation, my most favorite equation, once again, because we can use that to help predict whether or not a process is going to think about. That's pretty powerful. Notice they got the not sign. Okay, so these would be under standard conditions. Let's see. Oh, you notice they say 25 degrees Celsius. That's typically the temperature that's used. You guys notice that's like really close to room temperature. That's what has kind of been designated as standard temperature, because you think about performing in a lab, we might use a temperature pretty close to room temp. So you guys remember if delta G is negative, the forward reaction is spontaneous. Remember, a negative delta G means there's a negative loss in free energy, which is the total energy of the system, which is what you expect. You expect to go from a high energy situation to a low energy situation. If the delta G is 0, so when you calculate it and you calculate delta G is 0, you know what that tells you? It tells you the system is at equilibrium. Neither the forward reaction nor the reverse reaction is favored. And then if delta G is positive, the reaction is, gotta go through all those again, as you guys might expect, is, you really would say it is non-spontaneous. We're saying spontaneous in the reverse direction, okay? So it's not spontaneous in the forward direction, so therefore it must be spontaneous in the reverse direction. Okay, we got the enthalpy term, and we got, you guys remember this, the temperature is multiplied times the delta S, the entropy term. Okay, and you guys remember the temperature affects, right, this, the size of this, which is going to be ultimately compared to this to determine if delta G is positive or negative, is determined by the temperature. So how does standard delta G change with temperature? You guys remember we were talking about this? If you have an exothermic situation and entropy is increasing, when you plug those a negative term here and a positive term here, you're going to get a negative value. In those situations, it is always going to be spontaneous. If you have a situation where you have an endothermic reaction, which is a positive delta H, and a negative delta S, indicating you're getting more order, both those driving forces are going against what you would expect naturally, and when you plug those in, you're going to get a positive delta H, which would indicate it's non-spontaneous. But what if we get different values, like they're both negative and they're both positive? Then whether or not it's spontaneous or not is determined by the temperature. So that the size of the temperature is going to affect the size of this factor when you compare it to that factor, which will help you to determine, which will determine whether or not that's positive or negative. We talked about that before. All right. Okay, so you could do you could look up delta G values just like we did with delta H and delta S, and you basically get products minus reactants. So you could do that if you were working with delta G values from a table or so. Okay, now this is something, you guys, I went right to this, I didn't derive it, but what this is doing is, this is telling you how you would calculate delta G if you were in any other than non-standard conditions. So basically your delta G in any kind of condition, which ultimately is going to help you to determine whether or not the process or reaction occurs, is equal to your standard delta G plus RT, L, and Q. Okay, so you got a Q here, okay? You guys remember, right? You got, your Q is like, right, if you got your reactants going to products. You guys remember when you calculate your Q or your K, you take your concentration of products over that of your reactants, okay? So it says, use this equation if non-standard concentration of reaction species and you want to know if the reaction is spontaneous in the forward direction. Yeah. So we would have to, we're not going to actually use this form, by the way, but nonetheless, we would plug values in, and then we would see if our delta G was negative. That would indicate it's forward, it's spontaneous in the forward direction, and if it was positive, it is not spontaneous in the forward direction, it's spontaneous in the reverse direction. So under standard conditions, all concentrations are 1 molar. Remember we had stated that. So what would Q be? Well, you guys think about it. You guys remember how you get Q? You get Q, you just take your concentration of your products over the concentration of the reactants. Well, if all of your products are 1 molar and all of your reactants are 1 molar, you have a 1 divided by 1. What's your Q value? Your Q value would be 1. So your Q value would be 1, and then when you guys could write this on your calculator, when you take the natural log of 1, basically you just put in 1 and then you press the LM button. You know what you're going to get? The natural log of 1 is? It's 0. What's 0 times RT? It's 0. And so what do you find? Your delta G is equal to your standard delta G, which is what you would expect, because that's what standard conditions are, is 1 molar. So this should kind of make sense based on what we just saw there. Right, so Q is 1, L and Q is 0. 0 times this, that whole last term drops out, and so basically our delta G is the same as our standard delta G. Okay, So now we're going to kind of do a little derivation here, guys. So at equilibrium, let's say we're at equilibrium. Okay, so we're at equilibrium. There's no, the forward direction is neither favored nor the reverse direction, right? Because you guys remember these stay constant. So at equilibrium, Q, by definition, what do we call Q then? If it's at equilibrium, doesn't Q, we call it K, right? So it's K. And what is delta G at equilibrium? We learned from a few slides ago. If neither the forward nor the reverse direction is favored, delta G in that case would be 0. So basically what we're going to do is replace some things here eventually, okay? And so then we take the equation from the previous slide. So we put in a 0 for delta G and we put K instead of Q because we know it's at, under this situation. And then this is, we're going to rearrange it to solve for delta G. So we're going to leave that here and then subtract out that. This, you guys notice, is purple, so you guys mark that. This will be on your formula sheet, but this is something you guys want to have readily available. And so what this is going to do is, it's going to allow you to determine whether or not a process or a reaction is spontaneous, you guys remember, based upon the sign of delta G. If you're given an R value, which is a constant, I'm going to show you what the constant is. It's not the same constant as the universal gas law constant. Remember, that was 0.0821 liter atmosphere per mole Kelvin. This is a different one, but and then it's the temperature. You guys have got to remember, temperature always has to be in Kelvin. And then we get the natural log of our K value. You guys remember we get our K value by getting the ratio of products to reactants. So you guys, this is a very important, very useful equation. Yeah, I'm just kind of going back. Oh, okay. So here's the R value, guys, write that down. 8.314 joule per mole Kelvin. That is the value that will always be put here. So you guys are going to see, depending on what the K value is and the temperature you're at, those are going to affect whether or not the reaction is spontaneous or not in the forward direction. So now I'm asking, what relationship exists between G and K? Okay, so there's obviously a relationship. K obviously affects the Gibbs free energy, which ultimately tells you if reaction's favorable or not. Well, you think about it, right? If we get, you guys remember, right? If we have a K value that's greater than 1, think about it. If K is greater than 1, obviously the only way I'm going to get K greater than 1, like I'll change this to a K. K value is going to be greater than 1. When are you going to get a value that's greater than 1? When your numerator is greater than your denominator, right? So that your concentration of your products at equilibrium is greater than your concentration of reactants at equilibrium. So what does a K value greater than 1 indicate? That the forward reaction is favored, right? So think about that. So if K is greater than 1, which we already know that we already know that the forward reaction is favored from our understanding of equilibrium. So now if I put a number greater than 1 in here, if you take the natural log of any number greater than 1, you're always going to get a positive value. That's just what you get. So then think about it. You got a positive value times you guys know your temperatures in Kelvin, a positive value, that's positive, times negative R, which, so a negative times a positive will be negative. If your delta G is negative, what do we know about a negative delta G? It means the forward reaction is spontaneous, right? Which is consistent with what we just predicted. Think about the reverse. What if your K value is less than 1? So when you plug in equilibrium values and you plug it in and you get a number less than 1, what does that tell you? Obviously the only way you're going to get K value less than 1 is that the denominator is greater than the numerator, right? Which would indicate that the reactant side is favored. So it means that the reverse direction is favored and the forward direction is not favored or non-spontaneous. Let's see if that holds true. So if my K value is less than 1, I put this like, well, let's say it's 0.01 or 0.2 or whatever. I put if you get the natural log of any number less than 1, you know what kind of number you're going to get? You're going to get a negative value. So now I got a negative value times a positive, temperature always positive, that's a negative value, times a negative R, a negative times a negative is a positive. Now my delta G is a positive value, which once again, what does that mean? The forward reaction is not spontaneous, which is consistent with what we were just saying. We expect the reaction to be favored, it's favoring the reverse direction. All right, that's all we got, guys. Thanks for joining me. Until next time.